Ladies and gentlemen, all protocol observed, I would like to take this opportunity to thank you for listening to my presentation on groundwater parameters estimation for Nzoia Basin using NAM Mike 11 runoff model. I'm Stephen Mureithi, and I'm a civil and structural engineer from Kenya. So let's start by discussing groundwater as a key element of the hydrological cycle. So, as we know, groundwater is water that occurs below the surface of the earth, wherein it occupies all or part of the void spaces in geologic strata. These voids usually constitute of pore spaces in soils or fractures in rock formations. Normally, groundwater is only considered as water flowing through shallow aquifers. In the technical sense, however, it can also include soil moisture, permafrost, frozen soil, static water in very low permeability bedrock, and deep geothermal or soil formation water. So, the traditional definition of groundwater states that you look at it water as water flowing in aquifers. However, we can also say that once water has penetrated the soil, it can be considered groundwater. So that's what the statement means in a nutshell. So globally, the importance of groundwater cannot be overstated. It constitutes 98% of Earth's freshwater supply and currently provides a third of all total water consumed. This attributes for the water supply of about 2 billion people. It also supplies majority of water for agricultural and industrial use. In addition, groundwater provides a buffer against water shortages in droughts, effectively acting as a water reservoir. This is becoming more important, especially in the current weather fluctuations due to climate change. This is made possible by the fact that resident times for subsurface water may range from days to millennia. So, now we explore the link between hydrology and geology, which is commonly known as hydrogeology. So geography plays as a stage on which hydrology occurs. It plays key roles in determining how water will behave in a geologic system. For instance, only specific geologic formations can be suitable for groundwater. These include gravels, sands, the magmatic rocks, or karst. Therefore, geology will play an important role in determining whether an aquifer will occur, whether it will be confined or unconfined in nature. In addition, geography of an aquifer determines the water retention of that aquifer and the speed at which groundwater moves through the system. So the behavior of water in soil is also of utmost importance to the geotechnical engineer. For instance, the saturation and desaturation of clayey soil may cause them to expand and shrink. If a foundation is carelessly laid on such stratum, it may lead to differential settlement, which may lead to cracks in the building or structure, and thus reduce its aesthetic appeal. In severe cases, this may even compromise the structural integrity of the entire structure. Therefore, engineering hydrologists and geotechnical engineers cannot exist in isolation, but must use the knowledge from both fields in order to effectively do their work. So, now we state the problem, which is the complexity of groundwater estimation and data scarcity. Despite groundwater being so important, it is subterranean in nature. This means that it is invisible to the naked eye. Now, when you combine that with the fact that it has long residence times and complex underground routes and interaction with surface water, it makes it very hard to accurately estimate the and describe the behavior of this groundwater. So current methods of groundwater estimation can only provide a rough approximation of the behavior of groundwater, usually by giving rough values of recharge and extraction. This problem is often compounded by the scarce input data available on the same, particularly in developing countries. Currently, groundwater recharge estimation methods involve the soil-water balance, the Chatuvedi formula, seasonal recession method, also known as the Mayboon method, and the well-level data method. So the soil-water balance and the Chatuvedi formula rely on climate data. The Mayboon method relies on stream flow data, while the well-level method relies on observation well levels. Being in a sub-humid zone close to the equator, Nzoia Basin automatically demands for use of the soil-water balance method. However, the problem of data scarcity seriously plagues its use in the region. So now we promote my new technique, which involves the use of science, technology, and innovation, also known as STI, in groundwater investigations. So use of science, technology, and innovation provides an easier way for groundwater investigation techniques. Radar, sonar, and electrical resistivity methods, for instance, have provided a window into which you can peer into the ground data and get an idea of the water percolating within. Runoff models also give the ability to simulate the behavior of water in the hydrological cycle by the use of a computer. In essence, runoff models determine rules governing how much time water is estimated to spend at each time of the cycle. So therefore, the model is trying to describe the aquifer in terms of mathematical equations, so making it possible to write an algorithm completely describing the movement of water in the watershed. So these rules are known as runoff parameters when NAM is used. So the study seeks to determine the parameters guiding the flow of water in the hydrological cycle for Nzoia Basin, and therefore providing a reliable alternative for estimating groundwater. So this method is particularly important in basins like Nzoia Basin, coming from a developing country where data scarcity is a serious problem. So with such a simple technique, which does not use a lot of data, this alternative can be very useful. So my study area was Nzoia Basin, as previously mentioned, and I have delineated the basin from Rwambwa Power Point. And to do this, I used the ArcGIS program. So the area of the basin was found to be 12,640 kilometers squared, and geographically it lies between longitude 33.5 degrees east and 36 degrees east, and latitudes 1.5 degrees north and negative 0.2 degrees south. So the characteristic of that basin is Nzoia River, and in the basin are some important towns in Kenya, including Eldoret and Kakamega, among many others. So the highest point geographically is where the source comes from is in Mount Elgon, and another source is in the Cherangani Hills, Nandi Hills, and Kakamega Forest. So the river is about 330 kilometers from the source to the outfall in Lake Victoria, and the discharge into Lake Victoria is estimated at 1,777 million meter cubed per year. So the objective of the study was to determine the various soil, surface, and subsurface strata parameters governing the flow of groundwater recharge in Zoya Basin. So we go to specific objectives. To achieve this objective was, number one, to set up and calibrate rainfall runoff models for Zoya Basin. Number two, to determine performance of rainfall runoff model in Zoya Basin. And three, to establish groundwater flow parameters for Zoya Basin. So the methodology was simple. In the simplest term, we begin with data collection, which hydrologic data was collected, which was temperature, rainfall, and runoff data from the various stations. On collection, the rainfall, temperature, and observed runoff were to be checked for quality and manipulated appropriately by statistical analysis. It is, however, important to note that statistical analysis was the backbone for data manipulation and was used throughout the process. So what that implies was that statistics was very important throughout this project, not only for quality, but also was incorporated in other steps. So after this, a runoff model, in this case, NAM Mike 11, was then used to estimate ground flow parameters that best approximate our observed runoff from input rainfall and temperature data from Zoya Basin. So by logic, therefore, these parameters provide the best estimators for behavior of subsurface water in the region. So now we look at how the project turned out. In short, the results. So in order to input the data, we had to choose the stations. So these stations, first of all, we were chosen based on data taken from 1982 to 2009. This was limited by data availability, which again shows how scarce data for this basin really is. So rainfall stations were chosen based on a 90% completeness threshold. KO Marakwet was the exception at an 80% completeness threshold, which was added in order to improve on spatial distribution of these stations. So for temperatures data, on the other hand, we chose 3 stations, which were Kitale, Eldoret, and Kakamega. So for catchment delineation, we used Thesen polygons to determine area of influence of the various stations considered. This area of influence is important in future determination of the total average values affecting the entire basin. These average values represent the input data for the runoff model. Okay, so now we move on to the calibration of the runoff model. So the calibration involves changing parameters for Zoya Basin till the output that is simulated is similar to the observed discharge, that is from previous field observations. So once this is accomplished, this was accomplished by changing the parameters iteratively in order to obtain the best or optimal parameters. The best parameters are those that give the least root mean square error with the following conditions met. You do not exceed the maximum range of the considered parameters, and the water balance lies within 0.95 and 1.05. That is, the difference between simulated and observed values do not stray more than 5%. So during this process, it is important to note that there are specific model errors which are expected and which were observed, and these can be attributed to shift in the days, record errors from humans who are recording the data, missing values, and again the issue of data scarcity presents itself, and finally change in land use and land cover characteristics through the years, which may render these parameters less accurate. So now let's come to the ground flow parameters. So calibration achieved the task of giving us these ground flow parameters, which are divided into surface root zone parameters and groundwater parameters. So surface root zone parameters represent surface runoff and storage parameters of the basin in consideration. They govern the part of groundwater I had previously discussed before that is never considered, that is above the aquifer. So now these groundwater parameters, they define what is traditionally known when groundwater is being talked about. So they deal with the routing of groundwater once it has percolated into the water table and its recharge and loss into other systems. So yeah, so those parameters now they represent the behavior of groundwater. So if you think about it, think about those parameters as basically the representation of the behavior of groundwater in a representation of behavior of groundwater as expressed in a computer. So we go to conclusions. The use of NAM-11 model was found to be suitable for Nzoia Basin with R² between daily simulated runoff data model and observed weather station data meeting the threshold, which was 0.7. R² values comparing simulated data with observed discharge for the calibration period was found to be 0.9 for daily data. For the validation period, it was found to be 0.8 for daily data. And the optimal runoff model parameters observed were 12.7 for Umax, 136 for Lmax, 0.2 for CQOF, 1100 for CKIF, 62 for CK12, 0.25 for TOF, 0.2 for TIF, 0.05 for TG, and 25 for CKBF. So those acronyms that you are listening to are the individual parameters defining the behavior in groundwater. For instance, let's look at CK12. It determines shapes of hydrograph peaks, and so that means R² will be heavily dependent on these parameters, etc. So these gave a water balance of about 0.98 and a root mean square error of about 460. So this proves that the model parameters that gave the above results were suitably accurate in simulating the behavior of water upon precipitation. However, one-on-one correlation could not be achieved due to various model errors and uncertainties. So thank you so much for listening to my presentation, and I am open to any questions, and you can get back to me through my email mureithi@gmail.com if you have any further questions. Thank you.